In this learning video, we're going to look at mid-latitude cyclones and thunderstorms. Mid-latitude cyclones were the subject of this week's lab activity. And so if you've already looked at that instructional video for the lab, I've already talked about these mid-latitude cyclones and the different parts that make them up, the different features that are associated with them. But if you haven't, then this will be your introduction. Mid-latitude cyclones are a primary weather producer at mid-latitudes, thus the name. The mid-latitudes in the U.S. cross pretty much in the central part of the United States. And so in California, we're really not affected by these particular weather events. They're an idealized pattern of weather, just like we talked about the idealized wind patterns on Earth. They move from west to east across the U.S. as most weather does. They're first seen as approaching from the western sky. They require 2 to 4 days to pass over a given city or area. So here we are looking at a region from the south. So this is west and this is east. And so if you lived right here, if your city was right here, you would have a warm front approaching from the west. After that warm front passed, there would be a cold front that would approach and pass as well. Now, the further you are to the north, the closer these two fronts actually are to each other. And eventually, if you were far enough north, they would actually be touching and there would be an occluded front, and then all that warm air would be above you and you would have very stormy weather. So the warm front precedes the cold front, and the occluded front is where they meet. These events tend to occur in the spring when there's the largest weather contrast. And that's because in the spring, we still have cold, dry air coming down from Canada, and we're starting to get humid or moist, warm air from the Gulf of Mexico. And so these two air masses that are very different from each other, dry and cold, wet and warm, when they meet each other at the mid-latitudes, the fronts are very intense. And so the changes in weather associated with these air masses meeting create the mid-latitude cyclones. There are variations depending on the path of the storm. So this is from your lab, and it's showing the mid-latitude cyclone general shape. It's a counterclockwise rotating storm. There's the lowest pressure in the storm. Here's the cold front. Here's the warm front. And again, these are moving from west to east and also turning in a counterclockwise sense. Here's the occluded front section where the cold front has overtaken the warm front. Remember, cold fronts move faster than warm fronts. And so this section right here, GF, is a cross section that's shown up here where you can see that all the warm air has been pushed upwards in this region. Section A through E is shown down here where you've got the cold front, the warm front, and the region in between where locations C and D are. So we have the moist, humid, tropical air coming from the Gulf of Mexico, kind of in this direction. These are the wind directions. We have the continental polar air coming from this direction, and we have the maritime polar air coming from this direction. So those are the three air masses that are generally involved in a mid-latitude cyclone. If you were in City A and you were about to experience the entire pattern of this system, it would start with high clouds like cirrus clouds, and eventually as the system moved, you would get lower and lower clouds as the warm front approached, and then you would get a long period of rain, but not really intense rain. Eventually the warm front would pass and you would be in warm air for a short while. After that, the cold front would approach and you would get some very intense rain, possibly thunderstorms, and that's what we're going to talk about next. And then the cold air would pass and you would be in clear skies but very cold temperatures. This is just a reminder about these air masses I'm talking about. CP is coming down here. MT is coming up here. And so the cold front between them is located here. MP is up here, and so the warm front between these two is shown here. Here's a satellite view of a mid-latitude cyclone. You can sort of make out the states here. There's Texas, there's Mexico. You can see this counterclockwise spinning of the storm. The low pressure is probably about here. The cold front would probably be located about here in this picture. The occluded front would be somewhere up here, and the warm front would be somewhere out here. Here's a picture I took when I was teaching this very same subject in 2007. And that day there just happened to be a beautiful mid-latitude cyclone on our weather map. So I took a picture of it and put it in my lecture, and I've kept it in ever since. So here's a cold front, here's a warm front. The occluded front, for some reason, they didn't use the symbols that we typically use. But that's what that is. And then this is cloud cover. And then there's even a bit of snow here. This was in late November. I was just showing my students at that time, hey, look, there's one happening right now today. I just mentioned that thunderstorms occur at cold fronts, so let's talk about thunderstorms. So they are storms that generate lightning and thunder. So what is lightning? I have a nice picture here of lightning. And lightning is a type of static electricity. So what's that? If you rub a balloon on your head, then you're stripping away electrons from your hair, and they are transferred to the balloon. And then if you take that balloon and you put it against the wall, those electrons repel the electrons at the wall. And by pushing the electrons at the wall away, the wall winds up with a net positive charge, and that's attracted to the electrons on the balloon, and then they attract each other, and then the balloon sticks to the wall. Another example of static electricity is if you walk across a rug with your socks on, you wind up stripping electrons away from the rug. And now you have excess electrons on your body. So if you touch a doorknob, you get a little shock. And that's because those electrons don't want to be in excess anywhere. They want to be spread out evenly. And so that little shock redistributes the electrons. Lightning is an extreme example of electrons being redistributed. So in storm clouds, where there's lots and lots of wind blowing things around, water molecules have electrons stripped away from them, and the electrons build up in a cloud, for example, and there's an excess charge. And so that charge needs to be released either with another place in another cloud, or on the ground, or with a tree. And then that lightning that you see, that crackle, is the same as when you touch the doorknob, except it's 1,000,000 times bigger. And then thunder is the sound of that electrical discharge. So that's what lightning is, and thunder. And so you need big, stormy, windy situations for that to happen. Hail is also produced during thunderstorms. Remember, I talked about precipitation. And hail is the only frozen water precipitation that's not associated with winter. Hail is a springtime precipitation because it's associated with thunderstorms, and thunderstorms tend to happen in the springtime when we have these mid-latitude cyclones that generate thunderstorms. Thunderstorms are associated with cold fronts because we have rising warm air at the leading edge of the cold fronts. And I'm just reminding you here of that picture. Here's a cold front with cold air coming in from the left, and warm, moist air is being forced upwards and forming cumulonimbus clouds. And so it's right here at the leading edge of the cold front where we have those thunderstorms forming. So what are the stages of development of a thunderstorm? Well, the first stage involves rising air. And remember, when air rises, it cools, condenses when it reaches the dew point, and then it becomes clouds, rain. Remember that in this first picture, we actually do have a cold front here. Cold air is moving in, warm air is rising. And so this is the updraft stage, where air rising is the key to building the initial parts of a thunderstorm. And the bigger difference there is between this air and this air in terms of temperature and humidity, the more intense this stage is. That's why sometimes thunderstorms are really intense on warm summer nights. The next stage is when we have updrafts and downdrafts within the thunder clouds. These updrafts and downdrafts exist together. They work together to expand the cloud and to grow the storm, to make it larger. And any hail that's forming in here is going to continue to get circulated up and down in the cloud, and it's going to grow. Remember, hail is like a concentric ball of ice. Until it's too heavy for the winds to carry it around, it's going to continue to grow. Once it's too heavy for the winds to carry it up, it's going to fall. So this is the very intense part of the storm where the storm clouds will grow, and this is where we can have tornadoes, which we'll talk about in our next video. And notice that there's a little town here to indicate that this whole thing is moving past the town as it develops. Finally, it's moved past the town in this one. Now we no longer have any updrafts. Now we have passed that point, and now we just have downdrafts. And so this is the end of the storm. We have a light rain, but we're no longer fueling the storm with rising air. So those are the three sort of stages of thunderstorm development. Here's a picture showing the average number of days per year with thunderstorms. And you'll notice that there's a large region here in the Midwest where we have a lot of thunderstorms. That shouldn't be surprising because this is, again, where we have dry, cold air coming down from Canada and humid, warm air going up from the Gulf of Mexico, and it meets and creates fronts. We also have our mid-latitude cyclones creating cold fronts here. But I have a question. What's going on with Florida? Pause for a second and think about that. Okay, I'll tell you the answer. It has nothing to do with cold fronts. Florida has a large number of thunderstorms per year because of hurricanes, which are completely not related to cold fronts, and we'll talk about those in the next video. Some quick facts about thunderstorms. There's a whole lot of them every day on Earth. Lightning strikes Earth 100 times in a second, which is crazy. And thunderstorms and hail are very common in May and June because that is when we have the most common conditions for thunderstorms to occur. Coming next, tornadoes and hurricanes.